So power series. A power series is really just a way of writing some, literally it's something like the sum from k equals 0 to infinity, although really you can start at some other value. We often start at 0 of some constant times x to some power. So if we were to write this out, it would look like, sorry, moving things around here. It would look like just a sub 0 plus a sub 1 times x plus a sub 2 times x squared plus a sub 3 times x cubed, and so on and so on and so on. And often the question arises as to, does a certain power series converge or diverge on a particular interval? Or phrased in a different way, what is the radius of convergence? So for example, the following series, sum from k equals, I start at 1 to infinity of, to make sure I don't screw this up. Sorry, yeah, okay. And k of, let's say, x to the k over 3 to the k. Or someone might prefer to write the sum from k equals 1 to infinity of x over 3 to the k. We could totally figure out where, for what values of x this converges. So for what values of x does this converge? And the way we typically almost always do this is by using the ratio test. Technically, you could also use the root test, which we haven't talked about in this class, but usually the ratio test is the way to go. So to see where this converges, we're going to use the ratio test. And we're going to look at the limit. It's funny because I think with the ratio test, he totally uses n, right? Like he doesn't use k when he does ratio test. Like he does limit as n goes to infinity, or use limit as k goes to infinity. Okay, all right, that's fine. Fine with your k's. Limit as k goes to infinity of a sub k plus 1 over a sub k. Now, well, yeah, sure, we'll do this first. This is where we do definitely need the absolute values, because we're going to find x can be positive or negative. So we're going to get the limit as k goes to infinity of the absolute value of x over 3 to the k plus 1 over x over 3 to the k. Which is going to simplify pretty easily. If you have something to the k plus 1 divided by something to the k, almost all of them cancel out, and you're just left with x over 3 to the first. So this is the limit as k goes to infinity of the absolute value of x over 3. Notably, there's no more k's in my expression I'm taking the limit of. So as far as k is concerned, this absolute value of x over 3 is just a constant. I know there's a variable in there, but we're going to pretend like it's a constant as far as k is concerned. So as k goes to infinity, x over 3 is still just x over 3. So this is just going to equal the absolute value of x over 3. And then for us to get convergence, the limit of this ratio has to be less than 1. So we're going to say this is less than 1. And then if we solve for x, so typically here's, let me say, I'll tell you the work that you should probably do for class, but then I want to tell you kind of how I actually see it. So typically here at this point, you're just going to multiply both sides by 3. So you can say the absolute value of x over 3 is less than 1, or the absolute value of x over the absolute value of 3, which is 3, is less than 1. And then that becomes the absolute value of x is less than 3. And 3 there is your radius of convergence. But really the way I prefer to think about this is actually solving this inequality by saying, great, absolute value of x less than 3 means that x is between 3 and negative 3. And so the reason that's called the radius of convergence is because you're literally talking about how far from the center you can go to the left or right. So that's your radius of convergence, and that's your radius of convergence. Or alternatively, another thing about it is it's however long the interval is, 6 divided by 2. It's your diameter of convergence divided by 2. So when you're talking about where a power series converges, or really I feel like we don't actually talk about this in class. We more talk about the radius of convergence, right? Because there's this whole other thing that we're not going to get into about how technically you have to check the endpoints, because this certainly converges if this is less than 1, diverges if this is bigger than 1, and if it's equal to 1, the test is inconclusive. So you usually have to test, but we're not going to do that here, so I should stop talking about it. So when you're asked about the radius of convergence for a power series, let's look at 1 or 2 more examples. So let's say we want to find, and again, I believe that's what he's asking you about. Like, I haven't seen any homework questions, so I was looking at his notes, and those seem like the kind of ways he has been talking about this. So what is the radius of convergence for the sum from n equals 1 to infinity of x minus 5 to the nth power over n plus 7 times 4 to the n plus 1. I should also point out from that previous problem for just 1 second, this previous problem, this is totally a geometric series. Oh, that looks terrible. Right, this series here is geometric, where your ratio is just x over 3. And so you could totally say, oh yeah, it's going to converge when x over 3 is less than 1 or bigger than -1, because that's the usual criteria for convergence for a geometric series. This next one, definitely not geometric, right? We're not just multiplying by the same thing every time to get to the next term. We're going to use the ratio test. So whenever you hear the words find the radius of convergence, you should immediately think ratio test. That's the only thing you're going to do. So we're going to take the, and I used n because of course I did, right? So we're just going to do the limit as n goes to infinity of, okay, the n plus 1 term, so x minus 5 to the n plus 1 over n plus 1 plus 7 is going to be n plus 8. 4 to the n plus 1 plus 1 is 4 to the n plus 2. And then instead of saying divided by that, we're of course going to just multiply by the reciprocal. Say n plus 7 times 4 to the n plus 1 over x minus 5 to the n. And of course, we do need the absolute values here. Okay, so I'm not sure exactly how much work he's expecting to see, but I'm going to show you the work I would do if I was just trying to find the radius of convergence. So first and foremost, combine the like terms so that we can simplify this expression. We're going to have an x minus 5 to the n plus 1 over x minus 5 to the n. We're going to have an n plus 7 over n plus 8. And we're going to have a 4 to the n plus 1, 4 to the n plus 2. And then we're going to simplify. So we're going to rewrite this. Now you can probably skip this step and just simplify if you want to. So we're going to limit n goes to infinity of, well, that cancels out to just limit x minus 5. The n plus 7 over n plus 8 doesn't do anything yet. Its limit is going to be 1 though. So usually n to a power doesn't really contribute anything to the ratio test part of this problem. So this part's really just going to end up being kind of a nothing. So you're going to have n plus 7 over n plus 8. And then we're going to be dividing by a 4, right? Because 4 to the n plus 1 over 4 to the n plus 2 reduces to 1/4. So I'm going to put that there. And now as we take this limit, well, x minus 5 over 4 is just going to stay as x minus 5 over 4, right? There's no n's there. Whereas this part here, the limit as n goes to infinity of n plus 7 over n plus 8 is going to be 1, or 1 over 1 if you like. So then we get the absolute value of x minus 5 over 4. And here's something worth noting. Essentially, the coefficient of x is the reciprocal of your radius. So if I was to multiply this out, you can say that the coefficient of x is 1/4. And the radius of convergence is 4. Because we want that to be less than 1. And again, how you get from here to the end is kind of up to you. I would just look and be like, okay, the radius of convergence is 4. The center is, I know we haven't talked about yet, the center is 5. The center is always the number that if you substituted it in for x, you would get 0. So I can see that the center is 5 because if you plug in 5 for x, you get 5 minus 5, which is 0. So alternatively, if you want to actually solve this out, you can multiply both sides by 4, and say the absolute value of x minus 5 is less than 4. And then you could rewrite the absolute value inequality as x minus 5 less than 4, bigger than negative 4. And then adding 5 to everything, x is between 9 and 1. And so if you draw that on the number line, I think it's not too terrible to see that, oh yeah, the middle is certainly 5. Right? The average of 1 and 9 is 5. And then the distance to either endpoint is 4. So there's your center, literally in the center of the interval, and there's your radius. What to say about that? Oh, I don't think I have a lot to say. Questions? Thoughts? It's okay if you don't have any. I just want to make sure I'm not like forgetting something important. Yeah. That's kind of all there really is to about as far as finding the radius of convergence for a power series. It's literally just use the ratio test. It's kind of all there is to it. Which I know seems maybe sounds a little, I don't know what the word I'm looking for is. I feel like I'm making it sound easier than it might be sometimes, right? Like it's, yes, that's all there is to it, but it's still a process. So actually, let me hit you with 2 more examples because there are 2 things we should see. So one example we should definitely look at is, let me think for it now. Yeah, okay, fine. This example is lame, but whatever. Try and use K's again. Let's see. I want to come up with something better than what I was. I know you said fine. I want something better. I know he's done this example in class already. Fine, we'll change it up a little bit. Let's say we've got 2k factorial times x minus 1 to the k. And again, we want to know what the radius of convergence is. So radius of convergence and center. So I will point out, we should all be able to look at this series, this power series, as is written, and identify the center right off the bat. What is the center? 1, because if you plug in 1 for x, you just get 0 plus 0 plus 0 plus 0 plus 0, and that always converges. So a power series always converges at its center. It might not, and this one doesn't, converge anywhere else. So let's see why. So if we find, again, ratio test, I think it's good to write down the rate, like the words ratio test, so that I know I'm using the ratio test. Limit as k goes to infinity. Okay, I've got 2 times. Be careful with the 2k and the 2k plus 1 factorial. It really just has to be 2 times k plus 1, then the factorial of that. So I've got 2k plus 1 and then factorial times x minus 1 to the k plus 1 over 2k factorial times x minus 1 to the k. All in, of course, lovely absolute values. And then we simplify. So just as a reminder, 2 times k plus 1 factorial is 2k plus 2 factorial, which is 2k plus 2 times 2k plus 1 times 2k factorial. So over here in my fraction, I've got on top 2k plus 2 times 2k plus 1 times 2k factorial over 2k factorial. And then I've also got an x minus 1 because the rest of them canceled out. X minus 1 to the k plus 1 over x minus 1 to the k. And then the 2k factorials do cancel. I'm left with the limit as k goes to infinity of 2k plus 2 times 2k plus 1 times x minus 1. Still, I guess, in absolute value. So one of 2 things can happen here. if x is equal to 1, then you're going to get the limit of 0. Then we have the limit as k approaches infinity of 2k plus 1 times k plus 2k, sorry, 2k plus 2 times 2k plus 1 times 1 minus 1, which is 0 times something, which is just 0. And the limit of 0 is 0, which is less than 1. So if x equals 1, this whole thing converges. On the other hand, if x does not equal 1, then this limit's going to be infinity. Even if x is really, really close to 1, like 1.00001. A small number times something that's getting, right, a small number that is a finite, but like not getting smaller and smaller and smaller number, but they just like pick a small number. If you multiply it by something that's getting ever and ever larger, you're going to go to infinity. So if x does not equal 1, this limit as k goes to infinity of 2k plus 2 times 2k plus 1 times not 0, that's going to be infinity, which is certainly greater than 1. So we would say this converges at the center, and the radius is 0, right? You literally have no length to your interval of convergence. So the radius of convergence is 0. This one always feels kind of tricky because kind of like, and then you kind of have the opposite thing happening if you divide by something like n factorial or k factorial. For example, just to kind of show you the other way, because these do come up. Let me do that one. Yeah, I have a slightly better example. Let's say we have the sum from k equals 0 to infinity of, let me think for a second here. What is that? It's -1 to the k times x to the 2k over 2k factorial. Yeah. But just because I want to write it out so you can see it looks like this. It's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and the pattern goes on like that. And just because I might as well say it right now, this is equal. We're going to see this maybe today. What time is it? Oh, the clock is bothering me. It's okay. This is equal to cosine of x, which might seem kind of funky, but we'll talk about that in a minute, how we get there. This is the Taylor series for cosine centered at 0. And it converges everywhere. So the problem is, right, some of these expressions we're writing are only true for some values of x, right? Like if we go back over here for a second, well, I didn't actually say this, but I should say it. So if we look back at this first example, not only does this converge, we actually know what it converges to, right? This power series here is geometric, and it certainly converges to the first term over 1 minus the ratio. And so you could say that this function, which you could simplify, right? If you multiply top and bottom by 3, it's x over 3 minus x. This series converges to this function, but only if x is between -3 and 3. It doesn't converge if x is equal to like 5, which would be weird, right? If x was 5, 5/3 plus 5/3 squared plus 5/3 cubed plus 5/3 fourth doesn't equal 5 over 3 minus 5. That would be totally wrong. That's a negative number. So when we're talking about these functions converge, or these Taylor series for these functions converging, we're really talking about the values of x for which it makes sense to say this is equal to that. And for this kind of example here, it is true that it always converges. I mean, no matter what value of x you pick, you can say that cosine of x is equal to, cosine of 0.1 is 1 minus 1 squared, so on, so on. Why does this matter? Well, I mean, so why does it matter is kind of a tough question in week 10 of your last quarter of calculus at UC Davis. But the reason it kind of matters is because some functions you can't integrate. I mean, there's a lot of reasons why it matters. But like, for example, cosine of x squared is a function that cannot be integrated. But you could totally write a Taylor series for cosine of x squared and then integrate some terms of that to get a good approximation. So again, one of the reasons Taylor series specifically are pretty important is because they allow us to re-express functions that are maybe challenging as just infinite polynomials, which are easier to manipulate with differentiation or anti-differentiation. That's kind of one reason, to give you just some sort of reason behind why you might care about this, or someone might care about this. That's why you might. No, it's hard to care week 10, but hang on, you're almost there. When's your final? Okay, the first day of finals. All right, so okay. So again, convergence limit as k goes to infinity. You've got the k plus 1 term over the kth term, and here's what you're going to get. When I'm doing these limits, when you've got an alternating sequence here, I almost just never even write down the alternating part because it's inside an absolute value and it doesn't matter. Let me just put, I'll write it down, but it's gonna go away. So we're gonna get -1 to the k plus 1 times x to the 2, be careful here, times k plus 1 becomes x to the 2k plus 2 over 2 times k plus 1 factorial, and then times the reciprocal of that, 2k factorial over -1 to the k times x to the 2k. But then -1 to the k plus 1 over -1 to the k is just -1, but the absolute value of -1 you can pull out and it just becomes 1. So this doesn't matter. So we're going to rewrite this as the limit as k goes to infinity of, let's say I've got x to the 2k plus 2 over x to the 2k. And I've got, just like on the previous problem, I've got 2k factorial here. And we know that 2k plus 2 factorial is really 2k plus 2 times 2k plus 1 times the rest, which is your 2k factorial. And then those 2k factorials cancel out. This becomes x squared. So with the limit as k goes to infinity of x squared times 1 over 2k plus 2 times 2k plus 1. And this is where, again, you have to think about x just being any real number. So if x is 25, 25 squared is 625, and then as k goes to infinity, this part's going to get super duper small. So this is going to be 0 for any x, which means this converges for any x. So we get converges for all values of x. Or phrased another way, the radius of convergence is infinity. And the center is 0. Cool. So if the limit's always 0, it converges everywhere. Radius converges to infinity. If the limit's always not, or if the limit's like infinity, except for when x is at the center, then the radius of convergence is 0. Because it only converges at the one point in the middle, like in the previous problem. Cool. So again, that's kind of really most of how we deal with finding the radius of convergence for a power series, is by taking this limit of this ratio test and seeing what you get. So that means that for any value of x, you could, if you wanted to, write cosine of x as 1 minus x squared over 2 factorial, plus and so on and so on and so on and so on, which seems kind of silly, but again, there are reasons why we like to do that. So yeah, I feel like we should probably move on to talk about Taylor's formula, Taylor's theorem, same words. Taylor's formula. Maybe Taylor series. I imagine your professor has also thrown around the word Maclaurin series. Yeah. Maclaurin series is just when you're centered at 0. They're the same thing. Maclaurin series is just the special case. Trying to think of them. Yeah. So the idea is, for most functions, we would like to be able to write out that function as a Taylor series. It's not always possible to be done, right? There are some functions that it's kind of weird. Like there's some functions where you can find the quote unquote Taylor series, but the function actually isn't equal to the Taylor series. It's kind of a weird whole, very messy, minute, like subtle thing that we're not going to worry about at all. In general, we're just say like, can you find the Taylor series for this function? And the answer generally is yes. And the way you do it is you say Taylor series for the Taylor series for the function f of x centered at c is given by the following kind of long formula. It's going to be f of c plus f prime of c over 1 factorial times x minus c to the first plus, and then the pattern just kind of starts repeating. It's the next derivative over the next factorial times x minus the center to the next power. And you could go on and on and on and on, but of course we're not going to write this. That's why we have sigma notation. We're going to say this is equal to the sum from k equals 0 to infinity of the kth derivative of f evaluated at the center c over k factorial times x minus k, c x minus c to the kth power. That is Taylor's formula. And if it's Maclaurin, it's c is equal to 0. I have to say this the right way. There are lots of very well-known series Taylor formula expansions. I think your professors already talked about a few of them in class, but let's kind of just revisit them. So, some well-known Taylor series. So here's kind of the way I think about this. You're almost working backwards from looking at here's what something converges to, and then trying to kind of figure out the series that you started with in the first place. The most common example is this. The function 1 over 1 minus x. That looks like the sum of a geometric series. That looks like my first term over 1 minus my ratio. So I'm just going to tell you, here's the thing. There's this giant formula that's terrible to deal with, right? Like there are some really, there's some nice functions, which we'll talk about, but then there's some really heinous functions, like the square root of x. Doesn't seem that bad, but finding the Taylor polynomial for Taylor formula for it is really kind of gross. But the nice ones, there's kind of this expectation that you see them a few times, then you kind of just memorize them. And I'll try and get to where we're going with this. So this here is the sum from k equals 0 to infinity of x to the k. Now I know that because of experience, but you also kind of already know it. You know that this formula here, this geometric series, is equal to, well, let's see, it's 1 plus x squared plus x cubed. I could go on, but I don't really need to. But I just want to point out it is geometric. What's my ratio here? What am I multiplying by each term to get to the next term? Yeah, just x. So my ratio is definitely x. What's my first term? Definitely. So, oh yeah, this geometric series definitely adds up to the first term over 1 minus the ratio. Provided that the ratio is between -1 and 1. So for here to get convergence, we have to say, oh yeah, the absolute value of my ratio better be less than 1. So typically when we talk about a function being equal to its Taylor series, we also talk about where it is actually equal to it. Right? This is equal to that only if x is between -1 and 1. It's not if x is equal to 2. There's this whole, there's this whole like famous series, like this whole famous like branch of mathematics based on like what if x was 2, and then what would you get? And it's like there's this whole thing about like how like, yeah, I don't want to get into it. It's not what this class is about at all. But yeah, it's kind of interesting. Anyway, so here's the thing. We could have done this a different way. We could have done this the long Taylor formula, which I will show you because, well, I know he did this one in class, but it's worth looking at again. So the way people actually often do this is say, okay, here's my function, 1 over 1 minus x, which is equal to 1 minus x to the -1. And then they start taking, so the idea here is really, we want to find this part right here, because that's the formula for like the coefficient of x minus whatever to the k. So this function, which is centered at 0, we want to find the Taylor polynomial by finding the Taylor coefficient. So I'm going to start writing out derivatives. So there's a couple of different ways people kind of go. I like to just make a list of derivatives until I start to kind of see a pattern. And then I like to plug in my center. So here are my derivatives. The first derivative is going to be -1 times 1 minus x to the -2 times a -1 because of the chain rule. And I'm going to simplify this to be +1 times 1 minus x to the -2. And I'm going to note that every time I take a derivative, the negative I get from the power and the negative I get from the chain rule are going to cancel each other out. So let's just not write the negatives both times. So I'm going to say that my second derivative is going to be, now I will also tell you, it's often in your interest to not simplify. It's going to allow you to see the pattern better. So instead of just saying it's 2, I'm going to say it's 2 times 1 times 1 minus x to the -3rd. Again, right, the negative and the negative cancel each other out. And then my next derivative is going to be 3 times 2 times 1 times 1 minus x to the -4th. Then my fourth derivative, and the fourth derivative is where you usually start writing the derivative as a superscript in parentheses like that. My fourth derivative is going to be -4 times 3 times 2 times 1 times 1 minus x to the -5th times the -1. So it's going to be 4 times 3 times 2 times 1 times 1 minus x to the -5th. And now I think I see the pattern, right? No matter what number I have for my derivative, that coefficient there is that number factorial, which is why I wrote it that way instead of saying it was 1 and 2 and 6 and 24, because you might not see it as easily if you write out those numbers simplified. And then I can see that this power here is just my -4 plus 1. That's my -3 plus 1. So I could probably pretty confidently write the nth, or I guess I should say the kth derivative, because k, fine. K. So disappointed about k. It's kind of funny. So anyway, basically just taking my 4 and replacing it with k, I think my pattern is going to be that my kth derivative is k factorial times 1 minus x to the -k plus 1 power. But this is kind of the easiest example. Other examples where you do this, it can be harder to see the pattern after you've written 4 or 5 terms. I said 1 like I had a second thing to say here. 1, this is the easiest one. It's still kind of not super easy to see the pattern. And then after we see the pattern, or maybe before, depending on which, then we go and plug in our center. So we start plugging in c equal to 0. We see that f prime of 0 is just going to be 1. And f double prime of 0 is going to be 2. And f triple prime, well, I mean, I should just go straight to here, right? F triple prime of 0 is going to be 3 factorial. And then f k, the kth derivative evaluated at 0 is going to be k factorial times 1 minus 0 to the -k plus 1. But it doesn't matter what power I've got there, because 1 to any power is 1. So here's what this lets me do. This lets me take my Taylor formula and say, okay, great. My function, which is 1 over 1 minus x, which we said is equal to the sum from k equals 0 to infinity of the kth derivative at 0 over k factorial times x minus 0 to the kth power. Now I can substitute in that right there. So this just becomes k factorial over k factorial. So this ends up equaling, not surprisingly, right? We knew this was going to be the answer. The sum from k equals 0 to infinity of 1 times x to the k. So the point here is that if you start with just the function and you don't actually know the power series or the Taylor series or the Maclaurin series for it, you can use this process to find it. The problem is the process is unwieldy. Let me show you another example. Yeah, let's see. Yeah, sure. Let's say I wanted to find the Taylor series for 1 over 1 minus x squared. Still, again, centered at x equal to 0, centered at c equal to 0. I'm going to start off, but I'm actually probably not going to finish that way because you're going to see it's going to get gross. So I'm going to start taking derivatives. Oh, okay. And I should think of this as 1 minus x squared to the negative 1. So my first derivative is going to be negative 1 times 1 minus x squared to the negative 2 times negative 2x. Not liking this already. I'm going to simplify just a tiny bit and say this is going to be 2x times 1 minus x squared to the negative 2. And then my next derivative, already I want to cry. I don't want to do the product rule. 2 times 1 minus x squared to the negative second plus 2x times negative 2 times 1 minus x squared to the negative third times a negative 2x. Boo. Boo, boo, boo. And this is going to be just work, right? This is the second derivative and already it's gotten terrible. And even though I might start plugging in 0, like f of 0 is 1, f prime of 0 appears to be 0, f double prime of 0 appears to be 2 times 1, and that one's going to be 0 because there's a 0 there. But it's not going to be really easy to see the pattern here. So here's where people often go with this. This looks like another geometric series I just talked about. So what I'm really seeing here is that I have 1 over 1 minus some ratio. And I know that 1 over 1 minus some ratio, the Taylor series for that is going to be the sum from k equals 0 to infinity of my ratio to the kth power. Just like the previous example, right? We literally just said 1 over 1 minus x is the sum from k equals 0 to infinity of x to the k. Well, great. Replace the r with x squared. So 1 over 1 minus x squared is equal to the sum from k equals 0 to infinity of x squared to the kth power. And a power to a power, multiply the powers. So we can really write this as the sum from k equals 0 to infinity of x to the 2k. And so if you start writing this out, it ends up being 1 plus x squared plus x to the 4th plus x to the 6th, and so on and so on and so on. So what ends up happening, if we actually were able to continue this pattern here, every odd derivative would end up having 0 as the value when you plugged in 0, and every even derivative would just end up having a value of 1, I think. Well, no, no, not. It'd have a value of 2n factorial. Because really, the pattern that we were actually trying to go for was, the sum from k equals 0 to infinity of your kth derivative at 0 over k factorial times x minus 0 to the k. But finding this here, right, it's really not easy. So oftentimes what we do is we take known Taylor series and then we use those to find other harder Taylor series. Times it. Okay, so for example, so here's what I'll say. And again, I don't really know what his expectation is. Generally, the expectation typically for Taylor series is to memorize a few of them. So there are 3 that I think you should know, and I'm going to show them to you right now. I think that he already talked about them in class, but here's what I would say you should know to do problems on your test. And again, once we see the homework assignment, we might kind of refine what we're saying. But for now, I would say you should know the following 3. Well, actually, the one we just talked about. And then e to the x is my favorite. It is just 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so on and so on, which we could write in the condensed form, the sum from k equals 0 to infinity of x to the k over k factorial. What's super neat about this one is it is its own derivative, right? Just like we know that e to the x is its own derivative. If you take the derivative of this, all these terms, you get back the same thing, right? The derivative of x is 1, the derivative of x squared is 2x, and the 2 cancels the 2, and you get 1 factorial, and x, right? So on and so on and so on. There's 2 other ones I think you should know. They are sine and cosine. So sine is all the odd terms, right? Because I'll remind you, I know it's been a while Sine's an odd function. If you have the graph of sine for a second, it has odd symmetry. If you rotate it around the origin, it looks the same. And sine being an odd function means it better be an odd function. And polynomials are only odd if all the powers are odd. So sine is exactly odd power of x to the first minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And it just goes on and on and on. You get every odd power and the signs alternate. I find this one kind of a pain to write in sigma notation, but writing in sigma notation is the sum from k equals 0 to infinity. On top, we have a -1 to the k times an x to the 2k plus 1. That gets you every odd power, and then divide by that same power, the factorial. And then lastly, cosine is literally the same pattern, except it's even powers instead of odd powers. Now, one mistake I always used to make with cosine is I would always want to start with x squared, but we don't. We start with 1. So cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, et cetera, et cetera, et cetera. And then same pattern, -1 to the k, but then you get, instead of x to the odd powers, you get x to the even power, so x to the 2k over 2k. One way you can check this to make sure that you've written, or at least one maybe safeguard against making a mistake is, let me ask you both. What's sine of 0? And cosine of 0 is 1. What sine is 0? Right, but look, right, if you plug in 0 for x, you get 0 minus 0 plus 0 minus 0, right? It's 0. Whereas cosine of 0 is 1 minus 0 plus 0 minus, right? So cosine of 0 is 1. Oh yeah, that's smart. I just thought of that. I mean, kind of. Kind of cool. So for all of these, the radius of convergence is infinity. And then, of course, the one we just did, the radius of convergence is 1. So I should say, right, for the one on the previous page, so just as a reminder, 1 over 1 minus x equal to the sum from k equals 0 to infinity of x to the k. The radius of convergence is just 1. Or the interval of convergence is x between -1 and 1. So these are true all the time for any value of x. This last one's true only if x is relatively small. And it makes sense, right? X couldn't be 1 because 1 over 0 is undefined. So why do we care about these? Well, first of all, they come up a lot. But then we can use them to write other functions. So for example, people do some really weird stuff. Like someone might say something like, let me think for a second here. Someone might say something like, ooh, yeah, that's a good one. Find the, sorry, I'm just like doing weird stuff here. Find the Taylor series centered at 0. 0 is often the choice because it's easy. So I guess I could say the Maclaurin series and not have to write centered at 0, but oh well. For sure, f of x equal to x cubed times sine of x squared. There's no way in hell I'm going to find all these derivatives and plug in the center and find all the coefficients. What I'm going to do is I'm going to take my series for sine. You can't see. Take my series for sine and then replace x with x squared. So first, step 1, sine of x squared. Every x just gets replaced by x squared. So it's going to be x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial, et cetera, et cetera, et cetera. Which then we can write as in pattern. We're literally just going to replace the x there with x squared as well. So it's the sum from k equals 0 to infinity of -1 to the k times x squared to the 2k plus 1 over 2k plus 1 factorial. I'm really just replacing x with x squared. And then we can multiply it all by x cubed. So it's kind of interesting, right? So if you think about this, I'm literally just writing this as that. So if you start like, and again, I could simplify this a tiny bit. The negative 1 to the k. I should really be writing this as x to the 2 times 2k plus 1, which is x to the 4k plus 2 over 2k plus 1 factorial. I do like to think about actually plugging in k. So if I plug in k equals 0, right, I get 1 times x squared over 1 factorial, which is exactly that first one. If I plug in k equals 1, I get minus 1 times x to the 6th over 3 factorial, which is exactly the next term here. So it does work. And then if I multiply every term by x cubed, I'm just going to increase every power of x by 3. So x cubed times sine of x squared is literally just x cubed times all of that. Which just raises every power by 3. So I don't really want to actually do that, right? I mean, I could say it's going to be okay. It's going to be x to the 5th minus x to the 6 plus 3 is 9 over 3 factorial plus x to the 13th over 5 factorial. It's kind of annoying though. X to what? 14 plus 3 is 17. But really what I want to do is just take my pattern here and add 3 to the power of x. So that's going to be the sum from k equals 0 to infinity of negative 1 to the k times x to the 4k plus 5. Oh my God, 5 over 2k plus 1 factorial. Again, we can check if we want. If you start at k equals 0, you're going to get a power of 5. And if k equals 1, you're going to get a power of 9. If k equals 2, you're going to get a power of, oh yeah, that looks like it checks out.